The title of this talk is 200 is not always okay and how to cope with this. And I am your speaker, Rob Dickinson. I'm a VP of engineering at Graylog. I'm based in Boulder, Colorado, and I'm easy to find me online. Find me by email or contact me on LinkedIn. If you like what you hear here today or disagree with me or want to keep the conversation going, always love to talk about APIs. I talk about this stuff all day long. So yeah, reach out and let's chat. Um, Housekeeping point along those lines, if you have questions, you could put them in the chat at any point during this talk. You don't have to wait till the very end. Just go ahead and post when it occurs to you, and we'll be following up in real time. All right. So I'm a little bit of an amateur philosopher, which is not always meant as a compliment. Sometimes when my wife calls me a philosopher, it's usually more on the lines of let's get this done versus let's deconstruct this. But I do enjoy kind of these philosophical issues that we get into sometimes with technology, these ideas that we rely on that seem like they're pretty cut and dry. But when you really start to look at them more closely, you realize that they're a lot more nuanced and a lot more complicated than you may have thought. And HTTP response codes, I think, is one of those ideas that really turns out to be a lot more complicated than it seems at first. This is an important topic because a lot of observability tools, whether they're for web observability or API observability, but really anything that's looking at HTTP protocols, if you're over relying on response codes, that can really get you into trouble. And we can show you some specific examples here about cases where these 200s really are not okay. Now, I know what you may be thinking. You may be thinking, well, geez, Rob, that just doesn't sound right. I can go to Wikipedia, I can go to the Mozilla Developer Network, I can see, what these response codes are supposed to mean. And when I go to those sources and I read these things, it says that 200s means that things was okay, and that 400s means that there's a client failure, and 500s mean that there's a server failure. And isn't it that simple? Because that's what it says online. The reality is that life on the internet is not that simple. It is generally true that you can count on those 400s, those 500s to actually be problems. So those you can usually see. But if you're seeing a 200, that may or may not be okay. And you actually have to do quite a lot of work to understand if those were okay or not. And I think that's kind of a fascinating idea because it seems like this stuff should be really, really simple. But as you dig into it, you realize pretty quickly that things are not that simple. One of the ways that this shows up that can be problematic is if you think, well, because I have those simple definitions, because 200 means okay, and 400, range means client failure, and 500 means server failure, then if I count up all the APIs that I have, and I look at how many 200s they have, and I look at how many 400s they have, and how many 500s they have, that I should be able to score those APIs against each other or rate those against each other. And this is where that original idea about response codes starts to really break down. So you might think, for example, that the GraphQL API here, the first one in the list, is actually the best API because it has the most 200s and it has the fewest 500s. But you actually can't say that. Um, GraphQL just happens not to use 500 return codes as a matter of the protocol. We'll show you an example of that in a minute. So applications are not required to generate these 500s. It's a choice. The other thing that you get into is that so you're likely undercounting those threats and failures if you're looking at a distribution of response codes. and also the level of undercounting between those. So you might say, well, it looks from this like cloud is a little bit different than the license API, but you really can't say that either, because all that you know for sure is that failures are being undercounted on this application. They're also being undercounted on this application, but you have no way of knowing that they're undercounted at the same level. They might be running on different stacks. They might make different assumptions. So this kind of analysis, it's helpful if you don't have anything else to go on. But this kind of analysis is really not turn out to be the definitive measure of quality from an observability perspective that you might think when you're getting into this. This can also give you very misleading results if you're not hip to the reality here, which is these kinds of failures and threats are being undercounted. So, I hate just to show up and dump a bunch of bad news, but again, the reality is that we just can't, at the scale that the internet operates, we just really can't expect consistent signaling via response codes. The realities are that developers who are creating the applications, who are creating the APIs, they can use HTTP codes largely as they see fit. They also delegate some of that responsibilities because different frameworks have different built-in behaviors, some of which are modified by the developers, some of which aren't. So you have both the choices of the API designers themselves, and then also the choices around the supply chain that they use. The other thing that's true kind of about the internet ecosystem in general, APIs tend to return a lot more response codes. There's a lot more diversity in response code uses than you would see with websites. And partly is because browsers have historically not done a great job of dealing with different kinds of error handling. We'll talk about that in more detail. But when we talk about APIs, we're not talking about browsers. So we're not limited by browsers on the client side of this. So think about it then. So what we're saying is on the server side, the developers and the supply chain kind of get to make up whatever use of HTTP codes that they want. And then on the client side, it's not kind of the binary processing that we used to get with websites and web browsers. Can I render it or not? The API clients actually have a lot of control that's going on there. And so all this leads to, again, lots of these cases where you're going to see 200s on the wire that are definitely not okay. And here's a few examples. So GraphQL, as as the convention of how GraphQL works, what I'm doing here is I'm doing a post to a GraphQL endpoint, and what I'm getting back is a 200 OK response. And the response is that there's an error that the database is not responding. This is how GraphQL handles all error handling by convention. The response code is always 200 OK, and you're supposed to know if there was a problem or not by looking at the response. That is a specific, all the time convention that GraphQL uses. But REST APIs can also encode errors in the same way. Web pages can also encode errors in the same way. So this pattern is not at all limited to GraphQL. This is something that you see, all the time. Another example. Again, I'm making an API call to an endpoint. I'm getting back a 200 OK, and the response that comes back to me is a stack trace. So this is not a normal JSON response that I might be expecting back here from my REST API. And again, we see these kinds of silent failures happen all the time. And these look like they're okay on the wire. So, your web monitoring tools or your observability tools that are only looking at the request URL, the method and the response code are blind to these kinds of failures. And these kinds of failures are not infrequent. So it's really not uncommon to see again, at a system of any scale, it's not uncommon to see, a small percentage of calls that are doing this, on an ongoing basis, even for apps that you think are relatively healthy. Another example along those same lines. Here's another example where I'm doing an API request to an endpoint. The response coming back says okay. And if you look at this at first glance, you might think this is okay, but the super geeks will be quick to point out that this is actually malformed JSON. So we see this all the time on the internet. We see that these APIs are returning documents. They're returning JSON documents. Those JSON documents are built with code. They're dynamically generated. So that means that they're vulnerable to all those kinds of problems that you get when you're, generating documents. So maybe this was a null string and it got converted to an empty string and jammed in there. Maybe it was an escaping problem. It was missing the quotes. Maybe there were illegal characters that were included in this. Um, but if we took this and we put this into a JSON linter, for example, the JSON linter would point out that this is an invalid JSON payload because there's supposed to be a value right here before the comma. These can be terrible cases to try to find because a lot of these cases, the dynamic generation part of the code is breaking because it's data dependent or state dependent. So it might not be that it's failing this way every single time. It might be that it's only failing this way in rare instances, but those still turn out to be cases that you really care about from a quality or security or an observability perspective. And again, a traditional monitoring tool is going to look at cases like this and say, well, it must have been okay because it said 200. But clearly, the semantic convention between client and server here is broken, and this is definitely something that you don't want to be happening silently without being aware of it. Another example, and this one skews a little bit more towards security, um, which admittedly is a little bit, we're starting to get into a little apples to oranges comparison here. But again, consider the same pattern. So in this case, this is actually a malicious request. So this is an attacker that came along and said, give me this private hidden .env file. If you're dumb enough to serve that back to me, why don't you go ahead and give that to me, please? And we see these kinds of scraping attacks online all the time. So this is a very common way, you find that there's APIs running at Amazon, you know what the AWS IP address range is. You can scan that list of IPs looking for endpoints that are vulnerable. And this is a really good example of kind of one of those scanning attacks. Let's ask the endpoint for something that, if it's properly configured, it really shouldn't be giving me. Um, just in the case, that it does, that it's misconfigured. And that's exactly what's going on in this case. So that attacker is asked for this normally restricted file, restricted by convention, especially because on Linux or Unix, right, that dot file means this is a hidden file. And so we really don't want to be serving hidden files. But the backend, for whatever reason, is just happily saying, oh, yes, I can do that. Let me go ahead and give you the contents of that file. And again, we're saying that this is 200 okay. So it's a data leak, right? It's a scraping attack that resulted in a data leak. And your attacker is actually really happy if this says 200 okay, and your monitoring and observability tools are blind to this kind of case. But these things happen all the time. So hopefully, and I could cite more, right? But I hope those were a few, pretty compelling patterns that you could show. And of course, there's more variations and combinations of all those things. Um, it's a mess, right? And again, it comes back to that core idea. Generally, if you see a 400 or a 500, you can generally trust that. I really, if you're thinking of anti examples there, um, it's very rare to see something that actually is a 500 that is perfectly fine. Um, so that is actually the good news, or the glass half full statement that you can make there. Um, but when we zoom back from that, then, so if you accept that kind of we're in a bit of a pickle, we're in a bit of a mess with respect to these 200s. One of the most common questions that I've asked myself, and almost everyone asks when I start philosophizing about this stuff, is, well, if that's true and that appears to be true, then how did we end up in this place? Because, like, certainly the specs were writing stuff down and people were trying to do the right thing here. So kind of how did we get up, how did we get into this place? Is this a case where the standards were incomplete? um, did the standards change? Are they just not being are the standards just not being followed? Are the developers just being lazy? um, is this something that used to be true, but you can't really count on anymore? Or is this something that's really been there the whole time? Does the popularity of APIs now, and the fact that we've kind of taken browsers out of the mix, does that make things more or less reliable with respect to these 200s? Um, and so it's really interesting now to go kind of down the rabbit hole then, and kind of look at, well, how did we end up in this position? So if you go back to the core specs, especially the latest, the latest versions of the core specs, and you look for kind of the foundational definition of status code, I think this is the right thing to cite. And so what we're talking about here is that the 200 OK is supposed to indicate that the request has succeeded. Then there's some caveats, though. The first caveat that you see is the one that actually appears in the document, which says the content coming back in a 200 response depends on the method. So already, like, we're starting to hedge about, we just introduced this concept of status code as being succeeded, but then almost immediately you're saying, well, succeeded with respect to the meaning of the request method. But it's actually even more complicated than that, because there is actually no foundational definition of what we mean by success here. Success here is not formally defined. In fact, the intent of the specs in the early days was that it was whatever success meant between the server and the client. So this was very much just a contract between the server and the client, that the server can indicate success however it wants, so long as it's in sync with what the client's expectations are, and that contract is actually only between the server and the client. Only the server and the client actually know what that working definition of success is for that particular application. That sounds like a dodge, right? But that's the kind of flexibility that actually allowed the internet to gain, the universal platform footing that it has today. It was leaving some of those decisions to the applications that are running on these protocols. So even if you go back to, what you think wants to be the law that you're going to cite here, you're not going to find a strict definition of success that you can really hang your hat on. Um, the other thing that we saw, and we continue to see on the internet, for a long time, we've seen this idea that errors can be 200s. And one of the classic cases that everyone will recognize is the error page in that websites use. I just happen to be using the Disney one here because I'm a Wreck-It Ralph fan, but also because I can't think of a possibly more meta example of what we're talking about here. So this is a case where if you took a bad link into Disney.com, um, then instead of Disney giving you back a 404 error, which is rendered in your browser as just basically a blank page, which is a terrible user experience, right? Instead of doing that, the server gives you back a rendered page that is a 200 response code. And it's a 200 because your browser goes ahead and renders the content. So this is more helpful than just showing a blank page, right? One of the things you can do in your custom error page is you can have things like search controls. Um, you can have links to frequently asked questions. You can have contact information about how to get to support, all those things, right? This is not a new idea. From what I could find, the first custom error page appeared in 1993. So for a long, long time, we've had this idea that we're gonna take things like 404s and we're gonna turn them into 200s. And a lot of systems on the web work this way. And as you might expect, a lot of API systems that kind of inherited that thinking, like GraphQL, turn out to use basically that same idea. This just happens to be insanely meta because not only are we showing a custom error page that we're serving as a 200, but that custom error page also has an image where the image says 404. So now you're getting into like some inception level meta references. I mean, that's just crazy, right? It just makes me giggle as a nerd. Um, but you get the point. We have a long-standing history online of knowing that error handling was not the greatest aspect here, and taking a lot of those errors and burying them into 200s, which means we've always undercounted, these kinds of errors. That's why for an observability tool on the web, you really have to know what your error pages are because you want to be counting those. You can't just count them based on the response code. You need to count them based on the URL and the actual content that was returned. So since 1993. The other thing, and I don't have animations here, so it spoils the joke, but in a live presentation, I would like to say, the trick question, the number of response codes hasn't stayed the same over time, um, right? So the number of response codes has actually changed. This has never been quite the canonical thing that it says on Wikipedia today. But there actually weren't any response codes in the beginning, right? First spec had 0 response codes. You were supposed to know whether the response succeeded or failed by reading the response. That was the original pattern. And that works pretty well. Even into HTTP 1.0, which is where response codes first came into the mix here, we only had 14 response codes. And you'll notice there are no 500s in that initial grouping. For something like a 500 that was a server error, again, you were just expected to read the response and figure that out. The 300s and 400s were going to be signals to the browsers about when to ask for authentication, when to take redirects, things like that. So standardizing that kind of navigation handling, but not error handling, right? If you think about it. 500s didn't come in until HTTP 1.1, and that's when the number of response codes then explodes to 41, and then we added more on top of that in HTTP 2 and HTTP 3. So that is a large number of response codes to use. That's a large number to try to use consistently, and it's also, I would argue, too large a number to expect in a large number counting kind of case that you're going to see any, you know, really, really reliable consistency between how these codes are actually used. There's just too many of them. Um, And we should expect there's going to be more of those response codes in the future. So this is also a moving target. So yeah, there's a lot more complexity in the number of response codes than you might think. Um, but a lot of the history here, just like what we saw with that custom error page kind of idea, a lot of the history here was that if there were server side failures, that the client would have to read the response in order to figure that out and take the right action. So I think when you take all of those things and you put them together, again, I don't mean to be the bad guy. I don't mean to be the bearer of bad tidings, but this whole idea that 200s are not always okay, and that if we count 200s, we're probably undercounting the number of failures that we have. Unfortunately, we shouldn't really expect that to get simpler or to change anytime soon. Um, in some ways, I might wish that it would, but in my rational brain, looking at all aspects of this, like I just can't see a possible path where that would happen. Um, the number of APIs we already have today is in the millions. The legacy base that we have here, if we wanted to try to make something simpler, is the biggest thing on earth. um, we can't really expect all the API designers, even if we just said moving forward, we can't expect everyone to somehow magically synchronize and use the same ideas. Um, and when it turns out the HTTP specs, they never really intended to standardize the signaling to the extent of viewing that from a third party and scoring that from a third party perspective. I mean, what the HTTP specs really say is that, hey, if you're gonna indicate success, it'd be great if you could use 200 instead of 0 or -1 or like whatever other number you could think of. Like it'd be great if you mean okay that you could say 200. But it never actually legislated this is what okay means. That meaning of okay is very much between client and server, not so much from a third party observability perspective. Um, when you look at the intent of it, historically in pre API internet, the browsers were really good at rendering anything, but had really poor error handling apart from that. If you gave them a 400 or a 500, they'd show you a blank page. So for a long time, the browsers would kind of artificially restrict the use of response codes. They would encourage overuse of response codes because the browsers weren't great at handling anything other than a 200 okay. But APIs don't inherit those restrictions. With APIs, it's game on. So, however things might have seemed simple about how HTTP codes were used for web applications, really, there's no reason to expect APIs to be anything than incredibly more diverse and more complicated. The place where you will see restrictions show up with most APIs today is not going to be at the client because it's not a browser. The restrictions that you are going to be seeing put on it is going to be at the ingress controller, at the middleware, at the WAF, at the network, at the middleware between the client and the API endpoint. That's where you'll see some of those things getting refused. That's where you'll see some of the interpretation of HTTP codes becoming important again. Um, but again, it's not the client. That's more in the middle. So what we do as part of Graylog API security is we want to make it easy to help move beyond that concept of response codes and move to something that provides a more objective and easily comparable measure for your APIs. So we don't want to just talk about the philosophy. We want to put these ideas into practice. So in general, though, for somebody that's not doing any kind of reporting at all, it's not like using response codes is the worst idea ever. Like that, absolutely. If you're doing nothing else, right, then starting with summarizing your response codes is a great place to start if you have nothing else to go on. And you can assume that API failures there are undercounted. Um, that's okay. You can, you can put an asterisk by those numbers when you do that. But having some observability is always better than nothing. So start with that if you have it. What we do is we make it easy to get, jump beyond that. So we have a concept called response status, which is actually a measure of what happened with this. And that we're not relying on the response code to do that. We're actually calculating response status based on all of the requests and response details that we have. Response code is one of those details, but it's not the only detail. And then we're giving you a way to automatically calculate risk. So then we can compare APIs not just based on their volume characteristics, but by their total risk surface area. And this ends up being pretty simple. So even though there's a lot of philosophizing behind these ideas, the outcomes turn out to be pretty simple and easy to get your head around. So instead of, for example, when we're doing a quality measure, instead of breaking down response quality by response code, and using response codes to do that, we're using what we call response status. And you'll see that our definition of response status includes things like data leaks and malformed payloads, which are traditionally undercounted. And as you can see in this case, that is a significant number with respect to the number of completed transactions. So it's really not uncommon to see these kinds of things undercounted by 5%, 10%. I mean, not so large that they're blowing out your dashboards, but large enough that, do you care about a 5% conversion? If this is a revenue to generating API, like you probably do, even if they're in single digits. So again, it doesn't have to be horribly complicated to get a true sense of the result status and the response outcome of these API calls. We can then turn that into risk scoring, and we can then use risk scoring as a way to compare the APIs that we have. So instead of using response codes and distributions of response codes and having the asterisk of knowing that we're undercounting things, there's just a better way to do it. The better way to do it is just, and again, not to just look at purely the volume of this, because if you were looking just at volume, you might say, well, my public IP access to this API, where they didn't give a domain name, where they just went right to the API with an IP address. Well, that's a very low number of calls, but that's a pretty large percentage of the surface area, the attack surface. That's much greater than the volume would indicate. Um, so, our application actually has the greatest risk, and that's kind of what we hoped for. But we're seeing a lot more network attacks here than really if this API service was super helpful. We can also see things like rogue groupings, prohibited APIs we're not supposed to be using. If we have multiple API domains, which is not atypical, we'll be able to compare those against each other to know which are the problematic kids and which are the ones that are doing really well. And again, this is not something where response status or response code is the best vehicle to kind of get to an easy way to compare APIs against each other or to compare APIs against their past performance. But a risk scoring approach works really well. And we bring this out of the box with Graylog API security. The other thing that we're bringing out this fall, and this is new with API security version 3.7, is we're improving our discovery and our risk scoring with PII detection and analysis. We are contributing to and using the Filius open source library to do this. So this is an up and coming PII library where we're both a user and a contributor to this. And this library automatically detects at present 7 types of PII tokens that could appear in either the response or the request. We started with the types here that are more of the PCI types, right? So these are things like email addresses, credit card numbers, Bitcoin addresses, things like that. You know, those kinds of unique identifiers. We're automatically detecting those PII tokens during capture. We're indexing those. So then you can go back later and you can search. Give me the calls that had PII in the request, that had a credit card in the request. Give me the calls that had an email address in the response. So that data ends up being indexed, and then we automatically redact the original tokens as an automatic privacy measure. So all the data that's being detected with those types is automatically redacted, but we still have the ability to to know that that data was there and to be able to search on it. The other thing that we can do then is we can take that PII detection. We have new signatures that we're doing around these, and I'll show you an example or two here in just a minute. So there's new signatures then, as the system is now aware of PII types and how that PII data is flowing through your APIs. The other thing that we can do is we can automatically adjust those risk scores that I just showed you based on the PII types that are being found. And that is a very, very powerful idea. So yes, we have new ways to search, and yes, we have new kinds of signatures, but this is the next stage of that fundamental idea that risk scoring and now risk scoring with PII is really the best objective way that we can be comparing our API properties to each other instead of using those pesky response codes. So we're almost, it's Halloween season here. So of course, we wanted to put a little Halloween cheer in here. These may not be spider webs in the final version of how this is rendered, but here's one idea to get this across of what this might look like in version 3.7. So this is an example where we did a search. We're looking at search results, and one of the widgets that we can see in those search results now, and again, for any arbitrary search results, or any arbitrary summary. What were the types of PII that were detected in the request? What were the types of PII detected in the response? So we can see kind of what the coverage map looks like. We can see what kinds of data were showing up here. These are also refinable widgets. If you click into one of the points there, you would then be searching on specifically where email addresses were found or when phone numbers were found, and so on. Here's an example of what some of these new alerts might look like. And the one on the left here is really one of my favorites because I think it really shows the potential here. Um, so we've had this concept for a while of being able to detect completed attacks. And what we mean by that is we mean that a lot of these attacks, the attacker comes in and they bounce off with a 404. And there's not really a huge amount of damage done. I mean, unless it's a denial of service, but like you see a lot of those happen. They don't tend to do a lot of damage. You're not really interested in putting a lot of effort into mitigating those kinds of things because you're just always going to get, a lot of things bouncing off. But we've had this idea for a long time of completed attacks. So let's be able to zero in on this was something that absolutely fit the definition of being an attack signature but resulted in a 200. We can extend that idea now to say, let's look for completed attacks that also had PII coming back in the response. That is absolutely a very, very critical issue to be finding. And whether that's a data exfiltration kind of case, or whether that's a potential credential stuffing case, like on the right side here. Again, understanding the movement of that PII through the APIs turns out to be another really important way to understand what those 200s really mean. There are no error codes about privacy or PII, the existence of that. So another place where response codes are not going to tell you everything. So that's my talk. That's my time. I hope I gave you some good things here to chew on. If you'd like to see more about what we can do with API security, please come check us out. Thank you.